This video is titled Modeling Errors in IMPRINT. In this video, we will cover how to use the probability of task success to capture errors and automation failures. I've already created a new version of the model, and I have updated the description to note that we'll be capturing failures in this particular version. Now, oftentimes you want to model potential errors or failures in your model. When errors occur, the consequences often impact the subsequent sequence of events. In some cases, you can capture this through the branching logic of decision paths. For example, in an earlier version of our ATM model, we used probabilistic path logic to determine whether or not a correct withdrawal amount was entered. In a more recent version, we captured that same type of decision using variables combined with path logic. For example, when we went to model whether or not the PIN was entered correctly, we used a random number generator in the ending effect so that 95% of the time the PIN would be entered correctly and 5% of the time it would be entered incorrectly. We then used that information to update the PIN correct variable and used that same variable in our path logic to determine what the subsequent sequence of events would be. However, sometimes these options are not sufficient. This is especially the case when you already have complex branching logic handling the error-free situation. For example, suppose we want to capture the possibility of automation failures, where instead of accomplishing the required task, the ATM reboots without ejecting the card. We could do this by creating a task that would capture that, and I'll go ahead and do that now. So I now have a task that says ATM system reboots, and I want this to be an alternate end path. So instead of ejecting the card and the person taking the card, there are certain times when the system will reboot without ejecting the card, and that will end our particular scenario. Now I've created this path, and if I wanted to capture that this could happen in multiple places, I would then have to draw paths from each of those places where this could occur directly here, and then I'd have to add in logic into those decision nodes that are at the end of each of those different nodes to capture when this would occur. However, this would be problematic for a couple of reasons. First of all, the model could get very cluttered very quickly, especially if every single task node had the possibility of going into a system reboot. The other thing that's problematic is that we may already have complex branching logic, especially probabilistic logic, already in place, which would be impacted if we tried to then connect that particular task to the ATM system reboot as well. So alternately, we're going to handle this through failures, using the probability of success for the task. Each task has a probability of success, where the default is 100%. Thus, 100% of the time, the task defaults to being successful. However, we can modify this probability through expressions and directly updating the probabilities. When a task is unsuccessful, we can also set what the consequences of a failure would be. So notice that I currently have added this ATM system reboot task, and I do not have any nodes that are currently connected to it. It actually is permissible to have nodes in the model that don't have connections going directly into them. However, you may want to add a comment, for example, in the release condition, that explains how an entity would arrive at this node, since it's obviously not going to happen through the direct route. So I'll go ahead and do that now. For this example, I'm going to have it be that there can be an error when the balance check is unsuccessful. That would cause this particular ATM system reboot to happen. So in our particular case, it's going to happen after the system tries to do the balance check. So it's not going to happen before, but it'll do the balance check, and then instead of debiting the account or showing the balance, it will instead cause a system reboot. So I'm going to go ahead and go into that check balance node, and I'm going to look at the Calculate Task Success tab, which is there next to the Calculate Task Time tab. So note that there are 3 different ways that we can set the task success. We can use a probability, we can use a distribution, or we can use an expression. The probability is the probability of being successful. That is, if the task were performed 100 times, how many of these would be successful? Right now we've got all 100 that are successful. If we set it to 90, then 90 times it would be successful, and 10% of the time it would not be successful. We could also use a distribution. The way IMPRINT uses a distribution is it uses a normal distribution, and this distribution is different from task time distributions. What happens is you set a mean and a standard deviation on the accuracy when performing the task, and then you also stipulate an accuracy requirement. The lower your requirement, the greater the likelihood of success. So I'm going to go ahead and give you an example here. Generally these are between 0 and 100, so I could say that when the person's performing this task, their accuracy tends to be a mean of 60 with a 10% or a 10-point standard deviation. And then I'm going to say that my accuracy requirement is 60. And when I do that, you'll see that that updates that the probability of me meeting my accuracy requirement is 50%. If I had a lower requirement, like I only had a 50% of this task needs to be accurate requirement, but I have a mean of 60% of the task being accurate, then you can see that my chance of meeting my accuracy requirement is 84%. So this is a little bit complex because it's not a direct yes, no, I either was successful or I wasn't successful. The way this is working is that you've got an accuracy on the task itself, and you're trying to determine, was I close enough to consider it a success? I personally don't see the value of using this over during a direct probability. I definitely think it would be much more difficult to collect data on this particular type of information than to actually just collect data and look and see how many times did the person perform the task successfully versus unsuccessfully, and using a straight up probability. But if it makes sense for you in your particular case, that is how you would use this particular option. The third option, which I use quite frequently, is the expression. And this evaluates the expression to be either true or false. A true result means that your task was successful, and a false means that you have a failure. This is a great option to use when the likelihood of success is contingent on the current value of other variables in your model. So for example, let's say we collected some data and we found out that our system rebooted 3% of the time. We could then enter the probability to be 97%, because 97% of the time we were successful and 3% of the time we were unsuccessful. And that would give us our average for the system. However, if we delve deeper into the data, we might discover that our failures are more likely to occur when the funds are insufficient than when there were sufficient funds. Right? So recall that a failure is occurring after the system checks the balance. And so for some reason, when it goes to check a balance and it finds that it can't actually do the withdrawal because the balance is insufficient, we might have a greater chance of getting this reboot. So in my example, I'm going to suggest that if the funds are insufficient, we have failures 5% of the time, and if we have sufficient funds, the failure is only likely to happen 1% of the time. So the way I'm going to capture that is I'm then going to use an expression, and I'll go ahead and set that up now. So I've set up an expression where I am generating a random number because it's not guaranteed that it's not guaranteed that when we have sufficient funds we won't have an error, and when we have insufficient funds we will have an error. There's a probability on both of those. So I'm going ahead and pulling a random number that's between 0 and 1, And then I'm setting up the statement so it first checks for all of the possible cases where we might be successful. So if the sufficient funds are true, right, so we do have sufficient funds, and we then have a check for the random number if it's less than 0.99. So 99% of the time it will be less than 0.99. So if those two cases are both true, then we will have a return true here and we'll be successful. If the sufficient funds are false, so in those cases when we don't have sufficient funds, we then check for that random number if it's less than 0.95. So 95% of the time it will be there. And so we will have that case where we could also have a return true, which means we would have a success for the task. And then that 1% of the chance on when it's true and that 5% of the time when it's false, it will then default down to this else return false. And so we then would have those failures that 1% or 5% of the time, depending on what our case is. So that's one of those things, that's one of the ways that you could set up an expression. And then you can also embed some randomness along with pulling upon what are the values of other variables that are currently in the model. One thing that I'd like you to note is that there's a specific order to the timing of events that are happening within this task. So the very first thing that happens is the release conditions. The next thing that happens is the task time calculation, which is this here. And then the beginning effects happen. So since the task time calculations occur before the beginning effects, you can't set anything in the beginning effects that will affect the task time. You need to do that earlier. After the beginning effects have taken place, then the task time is executed. So if you have a task that takes 2 minutes long, that 2 minutes of time, those 2 minutes will pass after the beginning effects. And then we will calculate the probability of task success. So the task itself will execute before we determine whether or not we were successful. So there is an attempt. There's going to be a 2-minute attempt at that task. Then we calculate our task success. Now, given that timing, that means we can use items that are in the beginning effects. So for example, in this particular model, determination of whether or not there were sufficient funds happens as a beginning effect. So when we go into this task success, we will actually have this information updated correctly, right? So then it calculates the task success, and then after that, the ending effects occur. And these ending effects will occur regardless of whether or not the task is successful or not. So whether the task succeeds or fails, we're still going to have those ending effects occur. And then finally, we have the path logic that will execute. However, if the task is unsuccessful, then you won't necessarily have the same path logic occur. So now that we've set our criteria for when the task will be successful, we can now assign the consequences of failures. And that happens in the failures tab up here, two tabs over from the time and accuracy. So the default, as you can see, there's a 100% chance that there will be no effect. So the default, even if you set up some kind of failure, is that nothing really is going to be of consequence. However, we've got several different items that we can have happen. The first one is that we can have the task performance degraded. Right, so I'm going to fill that in. Note it's going to give me an error down here. Right, and so I can actually set the current task performance to be degraded, or I could set any other task. So I could have a future task be degraded. And I can either degrade it by time or accuracy. We haven't discussed accuracy yet, but you do have that option here. We can also change what the following task will be. So I'll set that back to 0. Go ahead and set that to 0 as well. And so we can make it so that instead of having the normal sequence of events happens, we can skip ahead to a different one. And of course, this is what we're going to end up doing. We can also set the mission to just be a failure if the task is unsuccessful. This doesn't necessarily affect the model directly. What it does is it affects the report outputs when it reports whether or not the mission was successful or not. We can also have the warfighter assignment change, and it can be on any particular task. So right now, I don't know that I've got that in there. There we go. So we can set, I do have multiple warfighters, so we can set a different person to perform any of either this task or any subsequent task. So that may be a benefit to you, especially if you want the failure to cause the person to no longer be available. And then of course we can also just have the task repeat. So if you want a failure to cause you to just redo the task, that's another way that you can apportion that. And of course, as you can see here, you can assign percents to any of these. So if you want just one of them to occur, then you can put in that 100%. Or if there's a probability that several different ones can occur, you can break that down and distribute that 100% accordingly. Note that down here at the bottom, it does sum the total, and if you try to do any sum other than 100%, it will give you this error message, because it really does want those all to add up to 100%. Of course, this also means that you can only have one particular error at a time, right? So you can't have both the following task change and do a task repeat. You've got to pick one or the other. Unfortunately, that's just the way this is laid out right now. So in our case, we're setting this following task will change, and we're going to change it to be that ATM system reboot, right? So now we go back to this task network diagram. Instead of doing the traditional path, when there is a failure, it's going to have the entity jump over to this ATM system reboot, and that will be the way that the entity will proceed from the model. And we've set that to be 100%, so whenever there's a failure, that's what's going to occur. So note that we can set failures to occur on tasks that are accomplished by either humans or automated systems. In this particular case, the checking of the balance is actually handled by the automated system. So this is one way to show degradations in reliability of your automation. And of course, you can also capture human failures as well. I also want you to note that every task can have a failure, and so I could take this particular scenario that I've set up here for the check balance, and I could make every task that the system performed have that potential to lead to a reboot. So I might change the validate ATM card, the authorization, and the debit and the show balance. So I could have all 5 of these result in a system reboot potentially. So if that were to happen and I were to collect data and I found out that there's a 5% chance that my system as a whole might fail, right? So per transaction, there's a 5% chance of a failure at some point in the sequence. I wouldn't want to go in and put the probabilities of each of those being 5%. Because, of course, the way probabilities work is that each of those probabilities would then be additive. So if there's a 5% chance of the validate ATM card failing, a 5% chance of authorized PIN, a 5% chance of check balance, and so forth, that would add up, those 5 would add up to then a 25% chance that there would actually be a system reboot. And so if I want to capture that there's only a 5% chance, I would need to up those probabilities in a way so that they sum to being the way the system actually is. And so ideally you'd go back and you would collect data and say, well, what's the chance of a reboot on the validate ATM card task? What's the chance that it reboots when it's trying to authorize the PIN? Right. And so once you have those smaller probabilities, those will then build to the probability of a system reboot as a whole. All right, so in this video, we covered how to capture errors and automation failures by setting the probability of task success and by setting the failure consequences.